You see a white blur racing through space at 58 kilometers per second, faster than anything we have tracked before. And here is what nobody talks about. The dust disappears, not over weeks, not over days, in hours. The comet throws particles into the void and they vanish like smoke in a hurricane. Why does it happen? What breaks the rules we thought we knew? 3 billion years drifting between stars, a surface weathered by cosmic rays, grains that crumble the moment sunlight touches them. The evidence sits in telescope data from July through October 2025, and it rewrites what we understand about ancient ice. Also, comment from which city you are hearing this from. This script is researched and factual, using sources from the James Clerk Maxwell Telescope observations published September 2025, NASA Hubble Space Telescope imaging analysis from David Jewett at UCLA published August 2025, and test recovery data analysis from Farnham, and colleagues published in research notes of the AAS in October 2025. These are not popular science summaries. These are peer-reviewed observatory reports with hard measurements. Now, back to the information. The Atlas Survey Telescope catches movement, 4.5 astronomical units from the Sun, an object with a hyperbolic trajectory. Eccentricity 6.08. Velocity at infinity 57 kilometers per second. Those numbers mean one thing: interstellar, not bound to our star. Just passing through after billions of years in the dark. Larry Deno at the University of Hawaii confirms it within hours, the third interstellar object ever detected. After Oumuamua in 2017 and Borisov in 2019. They name it 3I Atlas. The I stands for interstellar. The 3 marks the order of discovery. Everyone wants data before perihelion on October 29, when it swings closest to the Sun at 1.4 astronomical units. Because after that, 3I Atlas vanishes behind solar glare for weeks, and when an interstellar visitor shows up, you grab every photon you can. Hubble captures it from 277 million miles. David Jewett at UCLA leads the analysis. The image shows a teardrop shape, a compact nucleus wrapped in dust, but something is wrong. The dust extends toward the Sun, not away from it. Every comet textbook says radiation pressure pushes particles back, creates a tail streaming behind like hair and wind. 3I Atlas points the wrong way, a broad fan of material aimed at the star. Jewett measures it. The fan spreads 1 arcsecond long and 0.9 arcseconds wide. At that distance, that translates to 13 million meters by 1.9 million meters. The ratio tells the story. Dust moves faster toward the Sun than perpendicular to it, 7.5 meters per second versus the crossflow. The sunlit side heats up. Ice subliments. Water molecules rush off the surface carrying dust with them. Strong gas flux near the subsolar point accelerates particles harder than the weak peripheral flow near the terminator or on the night side. The result is a sunward fan, not a tail. A jet of material blasting directly at the source of heat. This has been seen before in distant comets like Bernardinelli-Bernstein. But 3I Atlas takes it further. By late August, the sunward plume persists even as a faint anti-solar tail finally develops. The inner coma, within 5 arcseconds of the nucleus, still looks fan-shaped and brighter on the sun-facing side in images from August 26. 60 kilograms per second of large particles with 100 micrometer radii. Total dust loss around 66 kilograms every second. That sounds like a lot until you compare it to typical Jupiter family comets at similar distances. 3I Atlas is quieter, less active, subdued. For an object warming up after billions of years frozen between stars, it barely whispers. Nearly a month of continuous imaging while the comet sat 6.4 astronomical units from the Sun. Adina Feinstein and colleagues stack over 9,000 frames. They search for an extended coma, the telltale fuzz that screams active comet. They find nothing. The radial brightness profile matches inactive asteroids. No extended envelope, no visible cloud of gas and dust, just a point source. The brightness implies coma hidden inside the central point spread function. Too compact to resolve, but present. That means dust was there, just not spreading, not creating the extended halo that marks typical comets. Tony Farnham leads a follow-up study published in research notes of the AAS. His team reaches the same conclusion. If 3I Atlas sustained activity during May and June, the dust must have been ejected at extremely low speeds, 10 meters per second or less, slower than anything standard models predict. Ice-rich particles that sublimate as they drift away from the nucleus. The surface brightness profile from Hubble steepens with distance from center. That gradient matches what happens when delicate aggregates break apart or evaporate in flight. The grains do not survive long enough to build an extended coma. They fade, crumble, disappear into vapor before they can scatter enough light to be detected from 270 million miles away. Webb turns its infrared eyes on 3I Atlas. Martin Cordner at NASA leads the spectroscopy. The coma glows with carbon dioxide, 129 kilograms per second. That dwarfs the water output, only 6.6 kilograms per second. CO2 dominates by a factor of nearly 20. Carbon monoxide adds another 14 kilograms per second. Carbonyl sulfide contributes less than half a kilogram. The ratios are bizarre. Most solar system comets spew water when they warm up. 3I Atlas bleeds carbon dioxide like an open wound. Either the nucleus really is CO2 rich, formed near the carbon dioxide frost line in its parent star system billions of years ago, or something blocks the water. An insulating crust, a thick weathered layer that prevents heat from reaching the buried ice below. Cosmic rays do that. High energy particles slam into surfaces during interstellar travel. Over billions of years, they strip hydrogen, alter chemistry, create complex organic compounds called tholins, reddish-brown material that absorbs heat but does not sublimate easily. Spectroscopic observations from X-Shooter at the Very Large Telescope in Chile measure the reflectance spectrum. The slope is steep, about 20% per 1,000 angstroms in the visible range. That is at least 1.86 times redder than Comet Borisov, the previous interstellar visitor. Redder means more processed, more irradiated. Santana Ross reports in August 2025 that 3I Atlas got even redder throughout July as activity increased. The surface, or coma, evolved in real time. Older material exposing as fresh layers, heated and released gas. Carbon dioxide, nitrogen, water, all can react under radiation to form tholins. These compounds create a non-evaporating crust, thermal insulation that blocks heat transfer and stops volatile ices underneath from sublimating. Only a small fraction of a comet's surface typically outgases. Most stays dormant. 3I Atlas could be almost entirely crusted over with just tiny active patches breaking through. Comparing that trajectory to expected paths of interstellar wanderers in the Milky Way, Hopkins calculates 3I Atlas could be 7 billion years old, older than the Sun, older than Earth, formed when the galaxy was younger and stars were poorer in heavy elements. If that holds, this comet drifted through space for 3 billion years before our solar system even condensed from its parent nebula. Knock atoms loose, drive nuclear reactions that change composition layer by layer. Hydrogen is the first casualty. Light, easily stripped, the surface becomes hydrogen depleted. That matters because hydrogen in water ice is what you need to create the bright hydroxyl emission that marks active comets. Without surface hydrogen, even if water sublimates below the crust, it does not produce the expected spectral signatures. The Swift Observatory detects hydroxyl on July 31st and August 1st, but the signal is weak, tentative, possibly from water ice grains sublimating beyond the nucleus, not from the nucleus itself. Analysis of Webb absorption features suggests water ice in the coma exists as fine grains smaller than 1 micrometer. These grains likely got ejected by outgassing carbon dioxide and carbon monoxide, not by water sublimating directly off the nucleus. The grains drift outward. Somewhere between 4,000 and 10,000 kilometers from the nucleus, they start to sublimate. That delayed sublimation creates a secondary source of water vapor and hydroxyl. But it also means the grains are ephemeral. They do not last. They evaporate into the coma and vanish. September 7th, James Clerk Maxwell Telescope in Hawaii measures hydrogen cyanide, 1.5 times 10 to the 25th molecules per second. A week later, on September 14th, the rate nearly triples, 4.5 times 10 to the 25th molecules per second, 2 kilograms every second. The cyanide coma stretches 180,000 kilometers across, elongated along the anti-solar direction. A dust tail 50 arcseconds wide appears in the same observations, 100,000 kilometers. Faint but real. The comet finally develops a proper tail 3 months after discovery, but even then, the tail is weak, diffuse, barely holding together. For a comet releasing 66 kilograms of dust every second, you expect a massive stream of particles reflecting sunlight across millions of kilometers. 3. Atlas does not deliver. The tail is a whisper. Earth. COM reports in August that the surface brightness profile from Hubble shows a broad fan-directed sunward, and only a weaker tail pushed away by radiation pressure. Modeling indicates dust launches toward the sun at tens of meters per second, but spreads more slowly perpendicular to the orbit plane. The pressure-swept tail is diffuse. The particles are large or fragile or both. Clearly visible despite being 50,000 times fainter than the Martian surface, TGO normally images, 5-second exposures. The nucleus itself cannot be resolved, too small, probably around 1 kilometer in diameter, but the coma shines, dust scattering sunlight. Yet even here, the full extent cannot be measured. ESA reports the brightness of the dust decreases quickly with distance from the nucleus. It fades into the noise in the image. The coma does not extend far, does not persist. It dies before it can spread. Keck Observatory adds another puzzle in October. Rohan Rahatgaonkar and colleagues publish a spectroscopy showing nickel emission, not just trace amounts, significant flux, but no iron. Comets sometimes release metals when organic compounds break down under solar heating. Nickel tetracarbonyl is one candidate, 4 carbon monoxide molecules bonded to a nickel atom. When it decomposes, it releases nickel vapor, but the process that creates these compounds in the first place requires unusual chemistry: space weathering. Cosmic ray bombardment over billions of years could drive reactions that incorporate metals into organic molecules in ways that do not happen in the solar system. A star with heavy element abundance at least 40% of the Sun, based on galactic thick disk membership. But even small amounts of nickel can produce detectable emission when the right compounds break apart. The lack of atomic oxygen, dicarbon, tricarbon, and amino radicals in VLT and MDM observatory spectra from July through August reinforces the strangeness. 3I Atlas is depleted in the molecules that make solar system comets glow bright. It is chemically distinct. A visitor from an alien system where ice and rock mixed under different rules. The wide range reflects the problem of separating nucleus light from coma light. Most of what we see is dust. Jewett estimates the nucleus radius at 2.8 kilometers based on surface brightness profiles. That implies a diameter around 5.6 kilometers. But if the nucleus is smaller and the coma is brighter than assumed, the true size drops. Vera Rubin Observatory estimates 5.6 kilometers, plus or minus 0.7 kilometers, from photometry in late June and early July. Bryce Bolin from Eureka Scientific uses Palomar Observatory data and arrives at 11.2 kilometers. The discrepancy shows how hard it is to pin down a comet hidden inside its own dust. The amount of material being released relative to the surface area that can produce it, even at 66 kilograms per second, 3I Atlas underperforms. Jupiter family comets at similar distances typically show higher production rates. This comet is holding back, limited by a thick crust. By low gas pressure under that crust, by surface properties that choke off sublimation before it can really ignite. Comets often brighten and dim as they spin, especially if their shape is irregular or their activity is patchy. The data shows no statistically significant period. Either 3I Atlas rotates slowly, taking many days per turn, or its activity is so symmetric that brightness does not change much. Or the nucleus is nearly spherical, unlikely for a comet, but possible if billions of years of sublimation in interstellar space slowly ablated away any protrusions. Activity increases gradually as it approaches the Sun, but no explosive releases of dust or gas, no fragmentation. Comet Borisov, fragmented, shattered into pieces. 3I Atlas holds together. That suggests internal strength, a more cohesive structure. Or simply lower internal pressure, because the volatiles driving activity are less abundant or more deeply buried. After perihelion, 3I Atlas swings past Venus on November 3rd at 0.65 astronomical units. 60 million miles, still not particularly close. Then out past Jupiter in March 2026 at 0.36 astronomical units from the gas giant. By then, velocity exceeds escape. The comet will leave the solar system forever, no return. A single pass through the inner solar system after billions of years in interstellar space, then back into the void. 8 days before closest approach. Hubble cannot observe, Webb cannot observe. Ground telescopes lose the comet in twilight. For weeks, it is invisible from Earth. Only spacecraft near Mars have a clear view, and even they struggle because 3I Atlas is faint. Magnitude 12 to 14 depending on the date and instrument. Too dim for most amateur telescopes, too dim for naked eye. Even with binoculars, you would need dark skies and luck. October 18th through 24th. The satellite sees objects down to magnitude 12. 3I Atlas shows up as a dim speck barely above the detection threshold. Mars reconnaissance. Orbiter attempts observations, but high-rise images have not been released due to a government shutdown. ExoMars. Trace, Gas Orbiter, and Mars Express capture what they can. Europa Clipper, Lucy, Psyche, Parker Solar Probe, Punch, SOHO, JUICE, all on standby. All hoping for data. Some get clear shots, others find the comet too faint or badly positioned. By December 3, I Atlas reappears on the far side of the Sun. Visible again from Earth, but fainter, receding, cooling, activity dropping as distance from the Sun increases. The dust production slows, the coma shrinks, the tail fades. And within months, the comet will be too far and too dim to observe, even with the largest telescopes. It will slip back into darkness, back into the interstellar medium where it spent billions of years before briefly visiting our small corner of the galaxy. Why does it fade so fast? 3 mechanisms dominate: grain fragility, ice-rich aggregates that sublimate in flight. The Hubble data shows this directly: surface brightness, profiles that steepen with distance, particles breaking apart or evaporating before they can scatter enough light to be easily seen. At 10 meters per second ejection speed, a grain traveling away from the nucleus covers 900 kilometers in a day. If it sublimates completely in that distance, it never forms an extended coma. It just vanishes. Small grains couple well to the gas flow and accelerate faster. Large grains resist acceleration and move sluggishly. But large grains also sublimate slower. They have more mass relative to surface area. They last longer. The tail that finally develops by September likely comes from these larger particles, the ones that survive long enough to be pushed back by radiation pressure. A crust that blocks heat and limits sublimation. Volatiles trapped under an insulating layer cannot drive high dust ejection rates. The result is subdued activity. Low gas pressure, dust grains lifted gently rather than blasted into space. Without strong ejection, particles do not reach high velocities. They do not spread far before solar radiation or sublimation or collisions destroy them. Either the comet spins with a pole pointing toward the sun so the night side never gets illuminated, or the surface has been dramatically weathered. The exclusive feature notes 3I Atlas is likely significantly older than the solar system, several billion years being bombarded by cosmic rays. That process strips surface hydrogen. Without hydrogen, creating a long, beautiful tail like solar system comets becomes difficult. The chemistry is wrong, the volatiles are wrong, the structure is wrong. If sustained activity occurred during May and June but produced no extended coma, then dust must have been ejected at less than 10 meters per second. Compare that to typical comets. Halley ejects dust at hundreds of meters per second during active outbursts. Even quiet comets far from the sun release particles at tens of meters per second. 3I Atlas barely manages 10. That slow speed means less time in sunlight before particles return to the surface or sublimate away, less time to build up density in the coma, less time to scatter light. The combination kills the coma. Fragile grains plus weathered surface plus low ejection speed. Each factor alone would weaken the dust envelope. Together, they strangle it. 3I Atlas releases dust every second. Hubble sees it. Webb sees it. But the dust does not accumulate, does not persist. It fades into the background faster than it appears. The result is a compact coma, a faint tail, an object that looks almost asteroidal in deep pre-covery images despite being clearly active in later high-resolution observations. New data from Keck Observatory confirms the antisolar tail, a nickel-rich, iron-free gas plume. TESS observations reveal faint or possibly inactive coma. Unusually slow dust ejection rates challenge standard models of cometary behavior. 3. IATLAS may redefine what scientists understand about the makeup and origins of interstellar visitors. Every assumption gets questioned, every model gets revised. This is not a typical comet. It is an ancient ice ball from another star system, weathered beyond recognition, barely clinging to activity as it passes through the warmth of our sun for the first and only time. Researchers simulate dust ejection from comets with various properties: grain sizes, ice compositions, surface temperatures, gas production rates, sublimation coefficients. The models that match 3I Atlas require specific conditions: low water content, high carbon dioxide content, thick insulating layers, porous structures with reduced thermal conductivity. When you plug those parameters into the equations, you get exactly what Hubble sees: a compact coma, a sunward fan, slow spreading, rapid fading. Measurements from missions like Rosetta to Comet 67P, Churyumov, Gerasimenko show comets have extremely low densities, around 0.6 grams per cubic centimeter. That is less than water ice at 0.9 grams per cubic centimeter. The difference comes from voids. Empty spaces between dust grains and ice chunks. These voids act as insulators. Heat does not conduct well through porous material. It takes longer for warmth to penetrate. Deeper ice stays frozen even when the surface heats up. Billions of years in space allow radiation to erode surface layers. Each sublimation event leaves behind a little dust. That dust accumulates, compacts, forms a lag deposit, a non-volatile crust that grows thicker over time. Eventually, the crust becomes centimeters thick. Measurements from Philae lander on 67P suggest dust layers up to 20 centimeters deep. Under that, hard ice mixed with dust. Under that, more porous material. The structure is stratified, layered, complex. Solar radiation hits the surface. The top millimeter heats up. But below that, temperature drops rapidly. By the time you reach a centimeter depth, the ice might still be well below the sublimation temperature for water. Only the most volatile ices like carbon monoxide and carbon dioxide can sublimate from deeper layers. Their sublimation points are lower, minus 128 Celsius for CO2 at 1 millibar pressure, minus 205 Celsius for CO. These ices can remain active far from the sun where water stays locked. But CO2 can still sublimate if it is mixed into the ice or if pockets of pure CO2 ice exist below the surface. When CO2 sublimates, it creates gas pressure. That pressure lifts dust. The dust carries embedded water ice grains. Those grains then sublimate in flight, creating the weak hydroxyl signal Swift detected. It is ejecting ice grains via CO2 and CO outgassing. Those grains then provide water vapor as they break down between 4,000 and 10,000 kilometers from the nucleus. That distance is large enough that the resultant coma is diffuse, spread out, low density. Hard to detect from Earth unless you are using sensitive instruments like Webb or Swift. For a comet at 2 to 3 AU from the Sun, surface temperatures range from minus 100 to minus 50 Celsius depending on albedo and thermal inertia. At those temperatures, water ice sublimates slowly, less than a kilogram per square meter per day. CO. 2 sublimates orders of magnitude faster. The difference drives the observed composition ratios. The active regions would be the CO2 patches. They heat up, sublimate vigorously, eject dust and ice grains. The inactive regions just sit there, absorbing sunlight, radiating heat, contributing nothing to the coma. If only 10% of the surface is active, then the true production rate per unit active area is 10 times higher than the average. That changes the interpretation of how strong the activity really is. Jewett notes the fan is broad but not symmetric. It shows structure, variations in brightness, that suggests jets, localized sources of gas and dust rather than uniform emission from the entire dayside. Jets form when sublimation concentrates at weak spots in the crust, fractures, thin spots. Places where heat can penetrate more easily, the gas rushes out, accelerates dust, creates a collimated stream. Multiple jets can merge to form a fan if the nucleus rotates or if the jets are closely spaced. If 3. I-Atlas rotates rapidly, the jets would sweep across the sky. Brightness would vary. The test-light curve would show periodicity. It does not. That means either the rotation is too slow to create detectable variations during the 20-day observation window, or the jets are aligned with the rotation axis. If the spin axis points toward the sun and the active regions sit near the pole, then rotation would not change the viewing geometry much. The coma would look the same from all angles, no brightness modulation. Some comets do orient themselves with poles toward the sun due to non-gravitational forces. Outgassing creates torque. If the outgassing is asymmetric, the torque can change the spin state over time. 3. I-Atlas has been active for a while, maybe months or years before we detected it. TESS saw it active in May at 6.4 AU. That is far. CO and CO2 can drive activity out there, but not water. The comet might have been outgassing on previous orbits in other star systems, or during its long interstellar journey, if it passed near massive objects that provided temporary heating. Fewer heavy elements, different chemical abundances. The CO2 to water ratio might reflect formation conditions we do not see in the solar system, or it might reflect processing. Billions of years of cosmic ray irradiation can alter ice chemistry, create new molecules, destroy old ones. The surface we observe today is not the surface that existed when the comet formed. It is a palimpsest, overwritten again and again by radiation and sublimation. He compares 3I Atlas velocity and direction to the local standard of rest. The motion suggests membership in the thick disk population. Stars in the thick disk are older, metal poor. They formed when the galaxy was young and turbulent. If 3I Atlas came from one of those stars, it has been wandering for billions of years. Maybe it got ejected during planet formation when a gas giant scattered it to escape velocity. Maybe a stellar encounter during a close pass through a star cluster. Maybe something else entirely. The key detail is time, 7 billion years in space. At typical interstellar velocities of tens of kilometers per second, 3I Atlas could have traveled thousands of light years, crossed spiral arms, passed through molecular clouds, survived radiation fields from nearby supernovae. Each environment leaves a mark. Cosmic rays alter the surface. Interstellar dust impacts create microcraters. Solar wind from close stellar encounters can strip the outer layers. What arrives at our solar system is a relic, a survivor, a fragment of ancient ice that somehow stayed intact despite hostile conditions. Add oxygen and you get ketones and alcohols. The mix creates a reddish-brown solid. Spectroscopy shows 3I Atlas has a steep red slope. That means abundant tholins, lots of processed organics. The longer the exposure to radiation, the redder the surface. Comparing 3I Atlas to Kuiper belt objects, which have been exposed for 4.6 billion years in the outer solar system, 3I Atlas is redder. That fits an age of 7 billion years. More exposure time, more processing, redder color. They affect sublimation. Tholin crusts are less reflective than fresh ice. They absorb more sunlight, but they also insulate. They do not conduct heat well. The result is a warm surface over cold ice. The temperature gradient is steep. The surface heats to minus 50 Celsius, while 1 centimeter below it is minus 100 Celsius. Sublimation happens only in the top few millimeters. Below that, ice stays frozen. Activity is surface limited. Production rates stay low. Researchers bury ice under sand or dust and illuminate it with lamps to simulate sunlight. They measure sublimation rates. The results are clear. Thick dust layers choke off sublimation. Grains must be ejected to expose fresh ice. But ejecting grains requires gas pressure. Gas pressure requires sublimation. It is a feedback loop. If the crust is too thick, sublimation stops entirely. The comet goes dormant, becomes a dead rock. The equilibrium is delicate. CO2 provides the pressure. It sublimates deep under the crust, where temperatures are still cold enough for it to exist as ice, but warm enough for slow outgassing. The gas diffuses through pores, escapes through cracks, lifts dust grains on the way out. Some of those grains are water ice. They sublimate in flight. The rest are refractory, silicates, organics, tholins. They do not sublimate, they just get carried along. 22 meters per second for 1 micrometer radius. That speed comes from strong coupling to the gas. Small grains have high surface area to mass ratio. Gas drag accelerates them efficiently. Large grains eject slow, 2 meters per second for 100 micrometer radius. That is because large grains have low surface area to mass ratio. Gas drag is weak. They barely accelerate. They also sublimate quickly because they are ice-rich and have high surface area. They fade within hours to days. Large slow grains stay near the nucleus. They form the dense inner coma. They also last longer because they are bigger and sublimate slower. They contribute to the faint tail that develops over weeks. By the time radiation pressure has a chance to act, they are already gone. Only the large grains survive long enough to form a tail. That is why the tail is faint and broad. It is made of survivors. The few grains that did not sublimate before radiation pressure could move them. The tail appears in Hubble images from July, but it is extremely faint, barely visible. By August, Gemini South sees it more clearly. 30 arcseconds long, 56,000 kilometers. Not impressive for a comet. Typical comets at that distance from the sun have tails millions of kilometers long. 3. I Atlas manages a tenth of that. The difference is production rate and grain lifetime. Less dust ejected, shorter grain survival, weaker tail. From 1.5 times 10 to the 25th molecules per second to 4.5 times 10 to the 25th. That is a doubling time of about 10 days. Exponential growth. The comet is heating up, approaching perihelion. Activity is increasing. But even at the higher rate, the cyanide output is not extraordinary. Solar system comets can produce similar amounts when they are closer to the sun. Radiation pressure and solar wind push it back. The dust tail aligns with the gas coma, 50 arcseconds across, 100,000 kilometers. Still small, still faint, but growing. As the comet warms, more ice sublimates, more gas flows, more dust lifts. The coma expands, the tail lengthens. By October, it should be more visible. ExoMars and Mars Express capture what they can. The coma is visible, but the tail is too dim. The nucleus is too small. The data is limited, partial, incomplete. The coma shrinks, the tail fades. The window for detailed observations is closing. By January 2026, 3I Atlas will be too far and too faint for most telescopes. Only the largest instruments will track it. And even they will struggle as the comet dims to 18th or 19th magnitude. The dust it shed will disperse, the trail will fade. Within years, there will be no physical trace of its visit, only data, only images, only spectra stored on hard drives and in archives. CO2, rich instead of water-rich, weathered instead of pristine, subdued instead of spectacular. The dust they release does not behave like solar system dust. It fades faster, disappears quicker, barely forms tails. The mechanisms are clear, fragile ice-rich grains that sublimate in flight. Weathered surfaces with thick, insulating crusts, low ejection speeds that do not give grains time to spread before they evaporate. Lies in wait for a pristine comet from the Oort cloud, or, if we are lucky, an interstellar object. When one appears, Comet Interceptor activates, chases it down, deploys probes, collects data up close. If the target is like 3I Atlas, the mission will see things we can only infer from Earth. Surface textures, grain properties, sublimation rates, chemical gradients, crust thickness. The mission will measure what we estimate. It will confirm or refute the models. It shows that interstellar comets are not just solar system comets with different orbits. They are fundamentally different objects, formed in different environments, processed by different histories, composed of different ices in different ratios. The dust they release reflects those differences. It does not persist like solar system dust, it fades like smoke. And that fading is not a failure of observation, it is reality. The grains are fragile, the surfaces are weathered, the ejection is weak. The result is a compact coma and a faint tail in a comet that barely looks like a comet at all. The rapid dust fading is the signature, the fingerprint, the evidence that 3I Atlas spent billions of years between the stars, that cosmic ray bombardment stripped hydrogen, that Tholen formation created a crust, that only the most volatile ices drive activity, that water is locked away under insulation, that grains ejected into the coma are delicate aggregates that sublimate before they can build density, that the comet we observe is not the comet that formed. It is a processed relic, an aged traveler, a ghost from another time and place. The numbers prove it. Dust ejection rate 66 kilograms per second, low for the comet size. TESS observations show no extended coma in May and June, despite brightness suggesting activity. That constrains ejection speed to less than 10 meters per second. Hubble shows surface brightness profiles that steepen with distance. That means grains sublimate or fragment in flight. Webb shows CO2 dominance, 129 kilograms per second versus 6.6 kilograms per second water. That means water is suppressed, locked away, not freely sublimating. Keck shows nickel emission without iron. That means exotic chemistry, space weathering, processes that do not happen in solar systems. Its dust fades fast because the grains are not robust. They are ice-rich, they are small, they are ejected slowly, they do not have time or durability to build an extended coma or a brilliant tail. They scatter light briefly and then disappear into the void. And that disappearance is the story. The whole point, the reason this comet matters. Rubin would have caught it earlier if science validation had started 2 weeks sooner. TESS saw it in May but did not recognize it. How many others passed through undetected because their comas were too compact and their tails were too faint? Maybe one per year passing within a few AU of the sun, but if they are all like 3I Atlas, we will miss most of them. They will blend into the background, look like asteroids, fail to brighten enough to trigger alerts. Only the closest or largest will stand out. The rest will slip through the solar system unseen, and we will never know what we missed. The composition told us it formed in a different place under different rules. The trajectory told us it will never return. This is a one-time opportunity, a single pass, a chance to study something truly alien. Not alien as in extraterrestrial intelligence. Alien as in foreign, different, other. Not from here. Photons from grains that no longer exist. It is archaeology, studying the dead, reconstructing what was from faint traces left behind, decelerating as it recedes. By March 2026, at Jupiter distance, it will be dim. By June, beyond Saturn, it will be invisible to all but the largest telescopes with the longest exposures. By 2030, it will be in the Kuiper belt. By 2040, in the Oort cloud. By 2050, back in interstellar space, alone again, silent, dark. Until perhaps in another 7 billion years, it encounters another star and briefly warms and sheds more dust and fades again into night. The spectra, the evidence. We know why the dust fades fast. We understand the mechanisms, fragile grains, weathered surface, low ejection speed. We see it in the numbers, in the profiles, in the ratios, and we know this is not the last interstellar comet. Others will come. Some will be like 3I Atlas, some will be different. Each will tell us something new about the galaxy, about planet formation elsewhere, about how ice and rock and organics mix in alien systems. Surveys are improving, telescopes are getting bigger, detection algorithms are getting smarter. In 10 years, we might discover interstellar visitors monthly. In 50 years weekly, each one a messenger. A sample return mission that brings material from distant stars directly to our telescopes. We do not need to travel light years. The comets come to us, and when they do, their dust tells the story. How fast it fades, how far it spreads, how long it lasts. Every detail is a clue, every measurement a piece of the puzzle. The dust of 3I Atlas faded in hours because it was ancient ice from an alien star processed by cosmic rays for billions of years and barely held together by weak gravity and low temperature until sunlight touched it, and it crumbled into vapor and vanished, leaving only data and questions and the certainty that somewhere out there in the dark between the stars are billions more just like it waiting for their moment in the light.